So without further ado, please join me in welcoming Matthew Bronski.
Thank you, Gretchen, and thank you everyone for coming out here despite the lousy weather. And it's really a thrill to help to christen this new BSA headquarters. Just a brief outline of what I'd like to cover tonight, a little bit of introduction about my project and how I came to it, the concept of architectural Darwinism, exegeses of 3 specific construction details that are very common in Rome and that I've picked out for tonight. A few brief words on efficiency and durability, and a bit about concrete durability as well. And then the general principles of durability that I've derived thus far from this work, and a few closing words. So I think everyone heard about Marcus Vitruvius Pollio in Introduction to Architectural History and Theory courses, but just a brief review. So born in the 1st century BC, died about 15 BC, and of course he was an architect, but at that time architecture encompassed a lot more than it did today. He was really an engineer, and that included structural, mechanical, environmental, and military, design of catapults and fortifications, an urban planner, and really a master builder and a foreman in a certain sense. And of course, best known for writing De Architectura on architecture, today often referred to as the 10 books. It's really more like one book with 10 chapters by today's standards of length. And it's really the only surviving treatise from classical antiquity, either Greek or Roman. We know that there were many others because Vitruvius tells us about them, and in fact he cites them and goes on to say how he's standing on the shoulders of those who came before him. And in a sense, his work is a culmination of all the previous works and his own thoughts and experiences. So if one book could survive from classical antiquity, I think we got the right one. My project really wasn't a study of Vitruvius himself, nor his treatise, nor his built work, of which there's only one that we know of, although there must have been many, and it's no longer extant. And it's not a study per se of how Roman buildings were constructed, but rather it's inspired by the methodology of Vitruvius, and in particular Book 2. And I think in a lot of the intro history and theory courses most of us had, we read quite a bit about Book 1, the qualities of architecture, the skills that an architect should possess, and further about the composition and proportions. But Book 2 is seldom assigned in those courses, and it's really about materials. And so what he did and charted in Book 2 was he went out and studied construction, both Roman and Greek, from previous centuries, some that had held up very well, and some that had failed and was crumbling already, and diagnosed why. And then he really developed and published these lessons learned as part of Book 2 for the benefit of the future professionals, so they could learn and so they could build more durably. And so it was that inspiration from Book 2 that led me to the project that Gretchen mentioned as part of my Rome Prize work last year. So my approach and goals were really similar, and they were to develop lessons learned both for rehabilitating existing buildings, historic preservation, and just rehabilitation of kind of run-of-the-mill existing buildings, and also for constructing new buildings more durably and hence more sustainably. It was funny, I was working with a contractor at Shawmut just before I left, and he said, well, you know, it's great that you get to go over in Rome and hang out for a year at cafes and all, but what are you really going to learn about durability? I mean, if we built buildings with massive stone blocks, 7 or 8 feet thick, our buildings would still be standing too, but we really just can't do that anymore. But hopefully there are a few lessons that you'll get out of this tonight, and certainly many that I got from Rome. So Vitruvius, as I mentioned, studied buildings from ancient Greek and Rome, and I intended to basically pick up where he left off, which is the 1st century BC when he published his treatise and when he died, and to really take that forward in time. So applying this methodology forward through the Middle Ages, the Renaissance, Baroque, and all the way up to 20th century modern icons, which actually constitutes a fair bit of my practice here in the Boston area. And I think we're pretty fortunate to practice here in Boston, where the building and construction history and architectural history runs so deep, really spanning 200 years and so many great architects who have worked here. But it was really an order of magnitude exactly off of what I was looking at in Rome, which was really spanning 2,000 years. And it was also a chance to test some of the things I'd learned and found over here in a different climate and with a whole different construction tradition. And here in the US, I have the benefit of a whole extensive lab at my fingertips and all sorts of fancy equipment and gizmos that we can take out onto buildings and do testing. So some of those you see here, ground penetrating radar and all sorts of calibrated equipment. But I really didn't have that benefit in Rome. I wasn't going to bring all this equipment there, and I wasn't even sure if they'd let me use it. Also, our work here in the States often involves making exploratory openings, because even with all the non-destructive testing equipment and the ground penetrating radar scans and everything else, there's still no substitute for seeing what's actually lurking beneath the surface. And I certainly wasn't about to ask, and I'm sure I would not have received permission to make openings in 2,000-year-old buildings. So that was off the table as well. So, well, what am I going to do? Or what did I do in Rome? Well, it was really purely visual, the methodology. And when I say visual, I mean looking, drawing, and thinking, and kind of repeating that cycle. And one of my colleagues once said when he was giving a lecture about all the non-destructive testing equipment we have at SGH and how to use it, don't forget the two best tools you have on any investigation are your two eyes. So just a few examples here. The upper right, that's a little shrine on the side of a church in the Trastevere section of Rome. If you look at that, you can see that roughly the upper third of that fresco, this is outdoors, by the way, roughly the upper third of that is really entirely intact. The middle third is about half there, half gone, and the bottom third is just completely gone. So this is really showing us the power of this sheltering roof overhead, protecting that from the rain. So it's not just symbolic, kind of a crown or an umbrella or a dome showing the importance of the shrine, but it's also very functional. Next to that, second from the right at the top, this is a street I just walk down every day, kind of a run-of-the-mill street leading down the hill to Trastevere. And if you look, there's a very dark line in the sidewalk about 1.5 feet off the building. And it's a line where all the mortar and the grit in the cobblestone or Pietrini paving has been totally eroded. And if you look at the top of that photo, you can see the roof edge matches exactly that height. So even though I'll talk later quite a bit about wind-driven rain, it's important to remember that a lot of the time, wind-driven rain is not a factor. It's not windy, or it's windy on the other side of the building, and this is the leeward side. And this water is dropping straight down. So that roof overhang is doing quite a bit to protect that facade from the weather. The large photo at the lower right, that's a building from the 1st century BC in the Roman Forum, the Curia. That's actually one of the few buildings from before the birth of Christ in Rome. And that stucco, every archaeologist and all the archaeology guides I saw swear that that is original to the building. And it's quite a large building, but if you can, we could have predicted that the only place it would survive, and that is the only place, is directly underneath that cornice where it's sheltered from the weather. The rest of the wall below this is just blank brick. And the two photos at the left are also kind of showing the power of sheltering a building from the weather. You can see this building had a red lime wash, and lime wash isn't particularly durable, although it has other benefits, and that's really worn off just about everywhere except underneath that roof. And even those subtle lines underneath the window hoods that are still dark red show that the window hoods are sheltering that area from the weather. Lower left, this is a streetscape in Venice. Could almost be any building in Venice, but the thing you can really notice here is that down very low, you can see the brick above the travertine water table. Those brick are intact, and they're pretty much wet all the time. Up above, say mid-height or upper part of those windows, those brick are intact too. So the brick that are always wet and the brick that are always dry are intact. And it's that drying zone in the middle where the salts are constantly coming up through capillary action and rising damp and then crystallizing through the surface that's blowing the face off all those bricks. So it's that intermediate zone that's really taking the punishment. At the right, upper and lower photos, that's a medieval tower in Lodi. And it was actually kind of reskinned at a certain point in its life, kind of late Middle Ages, early Renaissance. And you can see this, they're now doing a project to restore the tower. And if you look, you can see the skin separating from the main tower in that photo at the lower right. And by matching up the snapped headers, in other words, the brick that extended back from the new brick into the old brick, you can see how much this has moved. And this has actually moved about 3 inches. So we see this phenomena a lot here in Boston on early 20th century buildings, but I've never seen that order of magnitude. Usually we're talking about less than an inch, so 3 inches is just really extreme. The need for this research and this project, I see it as twofold, both in historic preservation and also in contemporary architecture. So first in preservation, we tend to focus our teaching and our research at two different scales. One is the micro scale, as you see here, how specific materials deteriorate, how they behave, and how we can restore them. So kind of the micro or the chemistry level of stone deterioration, mortar composition, etc. And a lot at the macro scale. What do we save and why? Why do we have a historic district? Why do we need them? Or at the building scale, the scale of an entire building, what are the important character-defining features? What is it important to save on the building and why? And we don't really focus too much in our teaching and research on the intermediate scale. So that is the scale of a window, the scale of how a roof meets a wall, the scale of a scupper, the scale of a bracket. Very little happening at that level. And in my experience investigating failures, that's really where it all happens. That's the scale at which buildings live or die in terms of their durability, is their detailing at that intermediate level. So these are all windows. Some of these were doomed to failure, and some of these were well designed for success. So these are all different windows that we've looked at. So it all comes down to the nitty-gritty details at that intermediate scale of how those different materials are assembled and thought through. And the need for this research in contemporary architecture, well, the way I see it, we're in the midst of a durability crisis in architecture. It's a pandemic of enclosure failures, and it really runs the gamut from high-end to low-end design and construction, renowned to unknown architects or even no architect on some residential projects, East Coast to West Coast, and many of these are just failing right away. So here's a hospital in Ohio in the lower left, kind of run-of-the-mill construction, no architect you've ever heard of. And we were on that building investigating failures and mold growth before the contractor had left the site, while they were punching out the building and before the hospital had moved into that new wing. Lower right are eaves, or better known as synthetic stucco failures, Drive It being one of the most common brands in the southeastern US, North Carolina, Georgia, etc., that were rampant in the mid-90s. So these houses were all less than 4 years old. Probably looked at 100 of these houses that were failing that rapidly, the wood sheathing and framing. And on to the high end, really a building in Cambridge right across the river that's probably no stranger to you. And across the West Coast, another building that I spent a lot of time on, the Thousand Oaks Civic Arts Plaza by Pradoc. And both were having problems basically immediately. And really the need, I see durability as fundamental to sustainability. So we've had a great deal of emphasis in the past 10, 15 years on sustainability. There really hasn't been much emphasis at all in durability, particularly among the relevant standards and scoring systems, LEED just being one of many, but obviously being the most common. And the savings or the advantages of durability are pretty obvious. Massive embodied energy savings of a durable material, a durable building over several buildings that might replace it in the course of its lifetime, and the reduction of landfill from all that demolition debris. So buildings like you see at the right in Rome, which are one's 1790 and one's 1550s, I believe, the Villa Medici, still going strong and still workhorse buildings after all these years, has an incredible savings in embodied energy over replacement buildings, even if we think of 100-year buildings as being some sort of pinnacle. Well, it would take 3 or 4 or 5 100-year buildings to replace these, and they're still going strong. So they must have done something right. So why this crisis in durability? Well, aesthetic innovation is one reason. It forces innovation in detailing, and it's possible, but certainly not easy, to always get it right the first time when you're inventing new details. But beyond that, I think we're forgetting some basic fundamental proven principles of designing for durability, and I'll discuss those a little bit later. First, the concept of architectural Darwinism, because I think this relates strongly to why traditional construction, such as I looked at in Rome, has proven so durable for so long. And in my practice on older historic buildings like the Old State House and newer architecturally significant buildings like the Holyoke Center at Harvard, I'm seeing more original design problems in the modern buildings than in the older historic buildings. So on the older buildings, you tend to see a lot of general degradation with time, old brick or old mortar kind of gradually weathering and eroding after a couple hundred years. But I'm talking about basic original design problems that are becoming manifest in the modern buildings. And I think it relates to this concept of architectural Darwinism. So when you see a highly evolved architectural and structural form, like a French northern high Gothic cathedral, these forms really don't arise instantaneously. It's not, you know, kind of a lightning bolt idea that hits someone, they draw it on paper, and they build it, and there it is. It kind of evolves in a series of little baby steps. So here's a very early Norman building in France. So you see the idea of the pointed arch. This is certainly not the tall, slender, unreinforced masonry building that you see at the right. It's a very squat, very heavy, blocky building. But it's a baby step in that direction. And if you look at cross-sections of Gothic cathedrals over time, so these go from top left to bottom right, you see them getting taller and taller and taller and more slender, which is very difficult to do structurally. So they're working that out over time. And it doesn't come without some bumps in the road along the way and pitfalls along the way. So Beauvais Cathedral alone had 5 collapses that are documented during the construction. So when we look at an ancient building that survived for hundreds of thousands of years, what are we really seeing? Well, we know that only the best survive. So in a sense, it's kind of a skewed population. The lemons are all gone. Mother Nature has weeded them out. It doesn't necessarily mean that when you look at a ruin, like the Baths of Caracalla at the lower left, that they were poorly designed, because other things come into play. War. A lot of these urban sites really just became quarries in the Renaissance. So hey, free marble. Let's go get some free marble. So that became the fate that was the fate that befell a lot of these. But when we do look at something that's intact, like Pont de Gare or the Pantheon or Maison Carrée, that are 2,000 years old, we really know they did something right. So I'd kind of sketch it up like this. Architectural Darwinism, you start out with a new material or a new form or a new method of building. Let's say the pointed arch, unreinforced masonry, tall and slender Gothic cathedral as a new form. There's a lot of trial and error. There are partial or wholesale failures, as at Beauvais. And then people learn from these failures. They learn both from failures on their own building and from what people are doing nearby during that same general period or style. And details and techniques evolve gradually that are viable. So then anything that survives is without serious original design flaws. They've either been changed or modified, or they learned from their predecessors and didn't make that mistake in the first place. And then a few hundred years later or thousands of years later, when we go to preserve or reuse or continue to use these buildings, we're looking at something that's fundamentally sound in its basic design. Now, working on a mid-century modern historic building like the Holyoke Center, we've really short-circuited this whole process. So we haven't had that time for evolution. We haven't had time to work out the bugs or learn from other similar buildings that had similar problems. And so you kind of just get into the point where a lot of the problems are starting to show 40 years later, 50 years later, as a result of all the weather and exposure. And at that point, you're trying to preserve them. So preserving these modern icons, I think, is more difficult in a lot of ways than the older buildings. And then the same basic graph is true in terms of kind of the rapidity of the evolution of new building materials. New building materials and components and systems are evolving so fast that we just don't have time for all the bugs to work out before, oh, that's something that people were doing 40 years ago and they're not building that way anymore. So we've moved on and the problems remain. So with modernism inventing new details, new forms for new materials, there's really no benefit of prior accumulated wisdom and experience. So 2 early 20th century houses here. The detail at left is from Philip Knobloch, a Pencil Points Press book, Good Practice in Construction. That's a fantastic book, and it's in reprint now, so you can pick that up. Has really phenomenal details. The detail, and that's just a kind of a representative house of that period that I snapped a photo of. So the house at the lower right is obviously the Walter Gropius house in Lincoln. So Gropius really wasn't, following this whole look, this whole way of putting a building together, of making a window, of creating siding, etc. So he had to invent a lot of his own details to do this, and ran into a lot of problems. So this window detail is highly problematic. It funneled water into the wall under it. All the wood under it rotted out. So we spent a lot of time helping the Society for the Preservation of New England Antiquities, now Historic New England, to restore that, and the windows in the area below them were a big part of the problem. So as the knowledge evolves, passing on the knowledge can take a couple different forms. It can happen through architects in a professional way, and that's how Good Practice in Construction, that book at the lower left, was written by a whole group of architects who got together and kind of talked about best practices, a lot of the leading New York firms of the early 20th century. And it can go through the builders as well. That's one of the foremen on one of my jobs in Rome, who passed on a lot of knowledge to me and who had learned a lot of knowledge from his predecessors. But what's often not understood today is why buildings and details look the way they do and how and why they work. So I'd like to take you through 3 different details and really break them down in terms of how they work. So, and these are just very, very common construction details in Rome that transcend several centuries, half a millennium. So the common facade forms, as you see at left, this kind of overhanging roofs, projecting band courses at the floor lines or ledges, window hoods and sills that project as well, and all that articulation of the facade. A very common window surround. This is a neo-Renaissance building from 1790. It looks a lot like Renaissance buildings from the 1500s, and even some early 20th century buildings still have window surrounds that look something like this. And a very common roof eave detail. You see that at right, really from the Middle Ages all through the Renaissance and on into the early 20th century. And of course, a lot of these things are imitated here. So the music building at the University of Pennsylvania, very nice recent restoration and addition by Ann Bea, has a roof eave detail almost exactly like this, like you see at the lower right. So our kind of Europhilic tendency, we've imitated a lot of these details over time. So let's start with the facades. I think it's easy to kind of look down a street like this, and a lot of early 20th century modernists did, and say, oh, we don't need all that stuff. Let's just simplify it and make it nice and clean and simple and plainer. However, these aren't just applied ornament. These are really functional. They're doing something for a living. So if we take a section of one of these buildings, so kind of the right image, the left, the brown section, all these appendages and all these projections, and just streamline it, make that perfectly planar, is there any consequence to doing that? Well, there is, because this is how water works in these load-bearing mass masonry walls. So unlike thin wall systems today that have a backup waterproofing or a drainage plane, I mean, this is all it is. It's a thick-walled masonry building, and our buildings in Boston, Beacon Hill, Back Bay, all the red brick buildings, basically work on the same principle, although they tend to be only about a foot thick. A lot of these buildings in Rome, the walls are several feet thick. But they work the same way. So if you look at the lower left, water comes in, and it has kind of a triangular gradient. So it's moving downward due to gravity, and it's also moving inward due to absorption and capillary action. So it creates that triangle. And what these ledges and band courses do is they catch that water like a flashing, and they direct it back out. So on the photo at the left, they're kind of resetting the clock at each stage, bringing that water out, and it starts all over again to avoid leakage at the interior. So at the far right, when you don't have that, then that gradient just continues to proceed inward, and at the point where that saturation hits the interior, then you have leakage. And you may see free water leakage, dripping. You may see plaster blistering, bubbling, that type of damage, badly peeling paint. And it's kind of an example of a building, an extreme example, I think. So this is a castle in the area outside Rome, medieval, 10th to 12th century. It doesn't have any of these things going on. It was a very utilitarian type fortification. So there aren't any ledges, there aren't any band courses. There may have been plaster, which would have reduced the surface area of this rough stone at one time, but there isn't now. And so that's a photo of the same corner, exterior right, interior left. And you can see that although it's only 2.5 stories, they're taking on tons of water right at that point. So without any of those devices, this wall, and these walls are about 7 feet thick on this building, aren't doing so well. And one thing that's important with the ledges and band courses is they really have to be detailed right to work. So they have to have a little bit of slope to the exterior, and just like a flashing would today, they have to go back inside the wall. So at the lower right, that's Ercolano Scavi. So it's one of the Roman towns that was buried by the eruption of Vesuvius in 79 AD. And I'd actually, if you go to Rome, I'd actually recommend Ercolano over Pompeii, even though Pompeii is more famous, because the architecture there is so much more intact. It's really phenomenal for someone who's interested in construction to see intact 2,000-year-old wood, wood framing and wood members, which you'll see at Ercolano and you won't at Pompeii. But at any rate, this ledge that you see at the lower right, here's a close-up on the lower left. It may be hard to see, but the cap tile, the kind of half-barrel shaped tile, you can see in that photo that that breaks off and it goes back inside the wall. And I can also see from these two pan tile, the kind of flat ones with the upturned edges, that those go farther back into the wall because they have a chamfered edge, the Roman pan tile, for the back 2 inches or so, and I'm not seeing that yet. So I know that goes at least 2 inches into the wall, and who knows how much farther, by the fact that I'm not seeing the chamfer. So if you look at the watercolor sketch at the upper right, that's basically what they did. And then think about what it would take to do that. The really easy way to do that, just like it would be today, is just build the whole wall, and then maybe fasten on a ledger board or something, and then hang that little pent roof or ledge on it. But they didn't do that. They built the wall up to that point, and then they stopped. And then they built that roof framing, they built the clay tile, and then they kept going with the wall. So it's less efficient, and that tells me that they really knew this was important. They were making the extra effort to kind of stop the process, build this in, and then continue on up. And it really does work like a through-wall flashing we would have today. That's the little tiny sketch in the top middle. So it's, again, catching that gradient of water by being deep within the wall because of the absorption, and then directing that back out. Window hoods, they also need to shed water like a roof, and they're also protecting a highly vulnerable area of the facade from leakage, and that's that head right where the window itself meets the window surround. And on Renaissance buildings, you tend to see a different shape of the window hood on the different floors as part of the articulation. Often it's kind of a pediment shape, a triangular pediment, semicircular or elliptical arch, and on some it's flat. And what I've tended to notice over time is the flat ones evolved over time. So you see a flat at the lower right towards this concave hip at the lower left. So they still had something that was a different shape. It was still distinguished from the other floors, but it shed water better. And then if you look at the ones that were flat, they've usually learned over time and been modified in some way. So this one at the lower right, there's a photo at the upper right of the same window. The stone was deteriorating, and they put a metal cap on it as a retrofit to try to keep water off it and shed water better. And that's Pecorino, kind of a low durability stone. The photo in the middle is actually the same building as at the right, but on a courtyard side where they have travertine windows. And there they've put sloped mortar topping on to try to get that water off the top of the windows. So both different types of retrofits to just try to improve the defect in the original design, which was the tops of those windows was basically flat. The sills are very critical. This is again the medieval castle in Ciciliano. And if you think about a very, very thick wall, typically it narrows at the window, both so people can walk in and get to the window, to increase the floor area, and also to allow more light into the building. So you see those two return walls at the lower left splaying out at about 30 degrees. So our whole idea of we have all this mass to absorb water and not let it get to the interior, the sills become very critical because they're much thinner. So the roof eave detail, the window surround detail, very typical both from the Renaissance and many periods forward. It's really well designed for water management, and I see this as an integrated design because the structure, the waterproofing, the architectural and aesthetic expression are all rolled into one here. So let's look at it piece by piece. Structurally, as we just talked about with the Ciciliano castle, the load is coming down from this mass masonry barrier wall. Whether you have an arch there or a lintel or a simple pediment, the load is going to be redirected around and down to the sides. So that's what we see here in the photo at the right. And that means in section, if you can see the section in the middle, the walls, as we just saw in the last photo, are going to get very thin just at that area of the floor line. In terms of water management, we talked about the band courses and the ledges catching the water and redirecting it out. So you see one of those at the top of the photo right, at the sill line at right, and then again at the floor line at the bottom. So those are all areas functioning to bring water out. The pediment, whether it's a triangular shape, a concave hip, or an arch shape, that's also directing the water around and getting it away from the critical window area and the critical sill. And then every little detail on the cornice and on these window hood elements is thoughtfully detailed. If you look at that center bottom photo, each of the moldings steps out beyond the one below. So everything is dripping water off and kind of clearing it of what's below. And if you think about the scroll bracket or the modillion that helps support that pediment, they're structural. They are helping to hold that up. They're also architectural. They're expressive. They're very beautifully carved in most cases. And they're kind of based on this precedent of the Roman temple, which is based on the Greek temple. But if you look at a Roman or Greek temple, like the Pantheon, which I have here at the top center, you'll recall that the columns are really at the outside of the architrave, right out there. And then if you look at a Renaissance window head, the structural support has been moved in. So that, again, is another device, as we see at the lower center, to help the water shed from that critical area where it's coming down. So a little refinement that makes it different than the temple precedent, but makes it better suited for water management. So in that photo on the right, let's say we consider point A and we consider point B. So they're points of the same height on the wall. One's on the window and one's off in the midst of the wall. What's going to happen with the water flow there? We're going to have some water coming down off that pediment head, but if we push point B out to the point where it's clear of it, then it's kind of more of a pure comparison. And at B, the area up above, some of that is going to flow down the brick on the face, and some of it's going to be absorbed into the brick. But at point A, the glass is impervious, so every drop of water that hits that window is going to wind up right at that sill. So between all that water being kind of funneled right to the sill, between the wall being very low at the sill, as you see in the sections at the right and in that photo from Ciciliano, something has to happen in the sill. What sort of magic happens? And then that also makes it no surprise that that area below the sill is stone, whereas to the right that's brick. You're funneling a lot more water to that point. They use the more durable stone to get the water from A down to that next band course where it's going to be shed from the facade. And so what do they do with the sill? So the wall's a lot thinner. We're putting a lot more water there. There's a lot of pressure for some magic to make something happen to keep this from leaking. And this was a really beautiful example from Palazzo Bronski. This is 1790, neo-Renaissance building. And I also saw it on a Renaissance building, the Palazzo Barberini Colonna, and on another building in Venice. So they have actually two internal drainage systems built into this window. So on the photo at the lower left, you can see there's kind of a line where the window would close. That's a trough, and it's in the travertine sill, and then it makes a T shape heading out to that little hole. So that's an outside drainage trough. So water that runs down that window is funneled there. It had a nice slope getting the water all the way out to that drainage hole. And then for any water that leaks through the window or any condensate on the window, there's an internal trough. So you see that as kind of the curved piece just slightly below, or maybe an inch below the window in the photo at left. And that's also in that little section sketch in the center. A curved marble trough, it's drilled through, there's a lead pipe inserted through, and it's actually soldered to the marble. So two drainage troughs. So then if you look at the photo at the lower right, you'll notice on the facade there's two little dots, and those are the weep holes where both of those systems drain. So you never really notice that, from the ground, and then you get up closely and look at it and see these things. And I thought this was really phenomenal, and thought it might be one of a kind, but then I did see something very much like it on two other buildings. So the lesson throughout here is not that the Renaissance window was brilliant and we need to design windows that look just like it. Well, that window was brilliant, but we don't need to design windows that look just like this. But we certainly do need to learn the principles that they embody, understand why they work, and then apply those principles today. So the two photos at right are a building by my friend Kiel Mo, who teaches at Northeastern. And the projection here is obviously in a very contemporary, modern vocabulary. Doesn't look anything like a Renaissance window, but I think it makes those principles of shedding and sheltering at the window very clear. So the third detail is the omnipresent roof eave detail from the Middle Ages on forward in Rome. So this is a really highly evolved detail. The function, the structure, and the architectural expression are all integrated. And someone might look at someone in the early 20th century might have looked at that, again, at that building section in the right image, the left brown section of the two, and say, boy, that looks really complicated at the roof. Can't we just simplify it and clean it up and make it like the gray one at the right? And I think it reflects a lack of understanding of just how much is going on with this detail and just how functional it is. So let's break it down piece by piece. Well, structurally, that main member that comes out and supports the roof overhang, the moment diagram on that is going to be a triangle. So kind of the shape it wants to be structurally is a triangle. And it wouldn't come exactly to a point, have a little bit of a blunt end because there is some, even though there's no moment in the end, there is some shear. And then the maximum moment would be back at that, at the deepest point of the triangle against the wall. And then if that element, that supporting element, were out in the weather and we're getting wet, the way it would rot looks like the middle one down on the right. So the water hits the end grain, it moves down through gravity, and it moves in through the capillary draw and the microstructure of the wood inward. So you get this kind of triangular shape of rot on this projecting member that's unsheltered. And I actually had a lot of exposed rafter tails on my own house that were rotted in exactly that pattern, so I can personally testify to that. And then the third one down is, okay, so what we need structurally is a triangle. The part that's going to rot anyway is the part of the triangle we don't need, so let's just cut that off. And then the one further refinement is, if that's just a simple sloping underside, if water does get to it, then we want to be able to get it off before it goes in again. So then you build in all these kind of little drip edges. So this, what looks like an ornamental piece, maybe at first glance, this highly intricate cut of that supporting member is really just perfectly evolved and integrated for the structure, the long-term durability, the architectural expression, and the water management. So some of these, and then overall, this is serving a great function of sheltering the wall from rain, and that's a principle we can really see, kind of throughout history and throughout Rome. At Ercolano, again, the 1st century AD, look at the size of this roof overhang. It must be about 12 feet. That's on a 1.5-story building. There's a section to scale at left and a photo in the center. Again, our photo of even that modest roof overhang on Via Porta San Pancrazio, 1.5 feet out, is still keeping water off that facade. And then when you get into the medieval period, a lot of times the mortar isn't as durable. They weren't using that much pozzolana. They kind of built with what they had. But probably as a result of that, you do see very, very huge roof overhangs on medieval buildings, and that's what you're looking at the top right. So the masonry wasn't as well built, but huge roof overhangs help to compensate for that. And when we think of those quote-unquote decorative end cuts, obviously they're not decorative and they're serving a function, but those go way back. So I was surprised to see just how far back those go. So that's at the bottom left, that's an original wood member from pre-79 AD at Ercolano, and there's a restored member on the same building at the right, so you can see the profile more clearly. But that idea has been around a very long time. And the very last point is, if you look at the watercolor at the right, notice the main supporting member, and then the rafters overhang that, coming down the slope. And then the wood stop at the end overhangs that. And then the tile overhangs that. So everything is overhanging everything else to kind of shelter that. You could draw a 30-degree line on that, and if you had even 30-degree rain, wind-driven rain, which is very, very extreme, that wood would not get wet. So they kind of did everything right. So if it does get wet, it's going to survive. And then they have this great roof overhang to really protect it and make sure it doesn't get wet. So, I was kind of amazed at first to see these Renaissance, medieval buildings, 500-year-old wood in Rome, in a climate where it rains a lot. It's hot and almost never freezes, which would help the wood be preserved. You see that in Scandinavia. But so a climate that's pretty severe to wood, and this 500-year-old wood in place, and those are a lot of the reasons. And then even something as hyper-specific is how far does that clay tile overhang that wood stop? How far should that go? That's thought through. And that's one thing I learned from Camone, who was the foreman on one of the buildings I was looking at, Palazzetto, the Little Palace, Cenci in Rome. This is actually the RISD program in Rome's building, and they were kind enough to let me on there. So he was the one that told me this, and this was pretty early on in the year when I was there. They were doing a roof restoration work. You see that at the left. And he said, yeah, when we overhang these tile, it's got to be 7 or 8 centimeters. That's about 2 3/4 inches. That's perfect, because if it's less than that, the water curls around and gets the wood wet, and we find the wood rotted. And if it's longer than that, when we come back out here, we find the tile is broken because someone leaned on it or stepped on it or put a ladder on it, and it was just cantilevered too far out. But 7 or 8 centimeters, that's perfect. It's kind of the Goldilocks dimension. So that was early on. Every time I got on a building, I put my tape measure up. So later I was on buildings by Bernini and Borromini. Sure enough, they were spot on. The tile overhang was 7 or 8 centimeters. So a few words about efficiency and durability, and just kind of a brief aside about concrete. I was really interested in looking at Roman concrete when I went over there, because I'd been working on all these concrete buildings in the US, that many of which are in really tough shape. So 1960s buildings, a lot of them are right around 1962 to 65. CERT buildings, Peabody Terrace and Holyoke Center at Harvard, the BU Law buildings, the Miami Marine Stadium, kind of fabulous structure that you see at the lower left, that have a lot of deterioration issues. And so why is that? Why can we have something like the Pantheon in Rome that's almost 2,000 years old, that's doing very well, and then we're having a lot of problems here with 40-year-old buildings? What can we learn? Well, I think it'd be glamorous if we could say there's this magic ingredient that they had in their concrete, and we analyzed it in our lab, and now we're going to use that in all our concrete, and we're not going to have any problems. But that really isn't the case. And what they had were a couple basic principles, and that is protect concrete from the weather. It's really that simple. Don't expose it. The Romans built extensively with concrete, and they almost never exposed it. And then don't reduce its durability by the manner in which you reinforce it. And they actually did have what I would consider a form of reinforcement. So if you look at Lancaster's book on Roman vaulted construction, she has good details and drawings on this. So something like the outer ring of the Colosseum, there were actually ferrous metal strap ties that take the thrust of the outer ring of arches. So if you think of a whole line of arches, the thrust from one offsets the next. But then when you get to the end, what do you do? You have a thrust that has nothing to resist it. So you either need something like a thick wall, or you need a buttress, or if you don't want that architecturally, then you need basically something like a tie rod. And what they actually use that's concealed within the construction of the Colosseum is something that's like a tie rod. And you actually see similar tie rods a lot on Renaissance courtyards and cortiles, since that inner ring is kind of unrestrained. So the Romans did have what I would consider a form of reinforcing, but they only used it where they absolutely needed it. They didn't kind of put it in there just for good measure. And protecting concrete from the weather, they almost always covered it. So this example I showed, that's original stucco on the Curia in the Roman Forum, And a lot of the residential buildings at Pompeii and Ercolano, you can still see the plaster facing on the brick-faced Roman concrete. And at the lower right, that's really the typical Roman construction. I mean, you'd read a lot about, well, the Pantheon's concrete, but the markets of Trajan, just all these other buildings, a lot of the Colosseum, other than that outer stone facing, are concrete, brick-faced concrete. So that's kind of a broken wall that almost gives you a pure section of what this Roman construction is like. And so how can we apply those principles today? Or, in looking at all these 20th century buildings, I've actually seen a couple that did apply them and that are doing quite well as a result. So out of the myriad of early to mid-1960s significant modernist concrete buildings I've looked at, the one that's probably far and away in the best condition is Morson Stiles College at Yale. So those are the two right photos. And Saarinen, what he did there, he was using a kind of a granite boulder facing almost that was cast into the concrete walls. So that was his way of being sympathetic with the traditional architecture of Yale. But as a result of that, those stones are 5 or 6 inches deep. The steel was set 5 or 6 inches deep behind the concrete. So instead of the typical 1.5 inches of cover, he had 5 or 6 inches of cover. And that's really what's made that building hold up so well, because the concrete quality is very similar to the other buildings I've looked at. So it's really the cover that makes that building in better condition than all the others. And at the lower left, this is Shangri-La, Doris Duke's mansion in Honolulu, 1937. It's all cast in place reinforced concrete. And before we went out there, I thought this was going to be an absolute disaster because it's right on the ocean. There's just salt spray hitting the building all the time. I kind of assumed they probably got the sand from the beach. It was going to be full of salt. And so all those things combined, I thought this building was going to be in pretty poor condition. And the concrete is actually doing remarkably well from what we could see. We didn't get to do any invasive testing or cores on that building, but there are really no signs of distress or spalling that we could see. And what they did there is just like the Romans did. They covered that with a stucco finish coat. So since day one, that's always been protected by stucco. And then the stucco's always been painted. So they had a layer of protection on there. And just a bit about efficiency. One thing that struck me in looking at Roman timber framing was how different it is than kind of early American, which comes out of the English tradition and which is also similar to French and German. So the photo at the right, or the image at the right from Abbott Lowell Cummings' text on the topic, just shows how intricate these connections are. And that's kind of the beauty of them, is just the handcraft that goes into them and how much labor goes into making these really intricate and beautiful connections. So they're often revered, but they do have some drawbacks as well. So, I mean, the deep cuts do weaken the wood member that you cut into. A lot of the structural failures we looked at in buildings like this tend to occur at the connections and at the cuts. Very time-consuming to build and inefficient time-wise, and I would say structurally because of the very deep cuts in the main members. The Roman tradition is very much different. So we didn't come around to the idea of just having one member sit on top of another member until late 1800s. And they were doing this 2,000 years ago. So if you look at the connections, say lower right, where these girts come into these main rafter members, everything sits on top of everything else. And there's really no shame in using a few spikes or nails. So they did that to keep those members from sliding downhill. So that's a connection in the center that just keeps those girts from sliding down. Everything is very simple. The only thing that's even more than just a blunt cut is at the top right, that kind of keystone connection at the top of this truss. So the other thing is members don't need to be exact. So things can kind of lap past each other, and there's not much precision that's required. So these were very quick to construct, and they're also very quick to take apart and reuse, and they're often reused. So so really they're just a lot more efficient as I see it for those reasons. And this is almost what I would call the Ochsendorf principle. So John Ochsendorf, who teaches at MIT, a brilliant structural engineer, he once told me that whenever he looks at a building, he always thinks that there's more to it than meets the eye. He shouldn't assume that the person who built it didn't know as much as he did. He usually assumes they knew more than he did. And I think if we looked at something like this photo at the right, a lot of engineers would say, well, they're using members on the flat, and that's not structurally efficient. It's much more structurally efficient to use a member like this rather than that. It's a lot stronger that direction. But, and that was probably my initial impression. But then when I thought about this more, the deck on these buildings does not brace these members in any way. So they have loose laid brick or clay tile. So when you look up in both these photos, and this is very typical, you will see either the underside of the roofing tile, it's really just structure and roof tile, or in some cases they laid brick as kind of a deck, but they're just sitting there and they're not even fastened except at the bottom, and then the clay tiles sit on top of that. So structurally what that means is the deck doesn't brace these members in any way. And so the members would be prone to buckling if they were like this. But by using them on the flat, they can't buckle. So there's actually a structural logic to what they did here that doesn't necessarily meet the eye. So it's just to the point that you need to really look at it closely and understand it, and don't just assume you know better. So building as much as they did and as far and wide as they did, the Romans were really all about efficiency in their construction. And I was really struck that their concept of efficiency, when I thought about it, is a lot different than our contemporary concept of efficiency in construction. So we tend to kind of think about specialization as the means to efficiency. So the assembly line model, the really influential thinking of Henry Ford, that everything should kind of go along, everything should be specialized. Each person or each part does one very particular thing. And I think that applies to our thinking in so many ways, even if you look at all the different positions on a football team and just how specialized each person is. But this assembly line model and the specialization model doesn't really work that well for building enclosures. Because if you have a complex detail like at lower right, and you often have a complex detail in a building with the 4 barriers, air barrier, water barrier, vapor barrier, etc. So to bring all those materials together in different ways, to make sheet flashing meet membrane, to make brick integrate with all these different materials, is basically impossible for the mason to come in, do his thing, and then leave, for the sheet metal worker to come in, do his thing, and then leave, for the guy putting up the membrane to come in and do his thing and leave. And that's what everyone wants to do. All these things need to be integrated. Sometimes one needs to lap over another, sometimes vice versa. The head can be different than the sill. So it just doesn't work that well. And sometimes we come up with tricks, to kind of make that work or bring people back when they don't want to come out to the job site more than once. But at any rate, it's a model that doesn't necessarily work that well. So the Roman concept of efficiency wasn't about specialization of every part. It was really much more about versatility. So for example, this really common Roman concrete construction that you see at the right, the brick there is doing a whole bunch of things. So the brick facing is the permanent formwork for the building. That's actually installed while the wall is going up. So rather than build a wall, build another wall, and then fill the middle with concrete, what they did was this concrete was kind of the consistency of peanut butter rather than the consistency of sour cream like we would make it today. So this was kind of a mound, and then they would drive brick wedges into it. So a lot of the tips are broken off, but if you look closely at those edge brick, you can see that they're all triangles. So those were actually triangular shapes that were driven into a very thick peanut butter-like concrete. Both sides went up at once, so it was essentially the facing and the formwork in one. And then it became another weather barrier, and it also became part of the composite structure because it was structurally monolithic. So 4 things in once. The Roman imposts, which are those elements at the base of the arch that you see in the photos at right, those were doing a lot of things at once too. So they're obviously an aesthetic and architectural expression, but they were also a logistical solution during construction that made the construction more efficient. So rather than, they needed a semicircular wooden formwork to support the arch while they were building it, but they didn't have to carry that shoring all the way down to the ground. It would sit on the lip of those imposts. So it's actually part of the logistics of building the arch that remains as part of the construction. And it's permanent and load-bearing. It's part of the architectural expression, and then it's there for repairs. If they ever need to make repairs, they can just put the semicircular formwork back in place. So general principles of durability. Here's a little quiz. So which of these shapes do you think would be a more logical and more durable way to build? So one's the pyramid and one's the inverted pyramid, both stepped pyramids. So, well, if you look at Egyptian or Mayan architecture, they'd probably go for the bottom one. If we looked at any of my daughter's toys, she would probably go for the bottom one. But I'm actually going to defy the logic of the Mayans and the Egyptians and Fisher-Price, and I'm going to argue for the top one, the inverted step pyramid. So why is that more logical from a durability standpoint and what I'm calling enclosure form finding? Well, if you think about the basic wedding cake or the step pyramid at the lower right, when it rains, every single surface is just getting soaked. There's no sheltering, there's no shedding, there's nowhere to run and nowhere to hide. When you think about the inverted stepped pyramid, you're sheltering the water, so in that little sketch, all those red areas are never seeing the rain, even in a 45-degree rain, and then each of those areas overhangs the one below. So the blue arrows are dripping off water, but even more importantly, they're not throwing it back onto the building somewhere else where it'll just be moving the problem around. By stepping out, every drip point clears the next one. So just a couple examples here of some modern buildings with those two configurations. Obviously Boston City Hall, then the bottom one is Thousand Oaks Civic Arts Plaza, which steps up a hill in a series of 5 or 6 steps. And you might think it's a modern idea, this kind of crazy upside down pyramid, but let's look not just at Boston City Hall, but let's look at the second oldest, I believe, house in Boston, which is the Paul Revere House, 1680 to 83. I mean, it has that configuration. I mean, it's not as exaggerated as I drew it in the sketch, but there it is. And then you start to look around at later houses, just run-of-the-mill historic construction. These are all just houses I drive by on my way to work. And you see that configuration again and again. And these are houses of different styles, and houses of the 19th century, houses of the early 20th century. And of course, how and why it works, very similar to the little sketch. So even in the 45-degree wind-driven rain, those green areas never get wet. They're always sheltered. And then the drops are always cleared of the area below, so they're not dumping the problem back on. And of course, you can tell from this kind of Tudor or Elizabethan-inspired house in the suburbs that it comes from English precedent. So you look back at England, here's a 15th century cottage, you see those same details, and this is just a worker's cottage actually, that photo at the very lower left. And it's also out in the countryside, so there isn't really the need to gain that additional space in a tight urban environment, because you do see that configuration in the cities. And the material, that's the center photo, it's actually a glass or plexiglass panel over one area where they have the stucco or the daub removed from the wattle and daub. The wattle is really just kind of woven sticks, woven reeds. So it's a material that isn't inherently durable. That's really not going to do well if it gets wet. And Vitruvius actually talks about this method of construction, and he really rails on it and says he just wishes it had never been invented because it's not durable at all. It's really terrible. It just falls apart. But the English figured out a way to make it work, and the way to make it work was with this configuration. And then you also see this precedent. It's a lot easier to do that in wood, but you even see this inverted step pyramid in masonry. So take a walk around some of the little alleys in Venice, and that's what you're seeing at the lower left, and you'll see this all over the place. So even masonry buildings, they're stepping out, sometimes with wood framing, which is actually common in Rome, and you do see that at Ercolano as well, sometimes with stone brackets and corbels. And this building at the right, which I found really interesting, they're doing it in both. So you see these huge wood beams very closely spaced, but then where they have I imagine where they have a demising wall, then they have this huge stone corbels as well, 4 of them across the facade, stepping out that facade. And also you see the projection of the window hoods, the window sills, all those elements to shed water, particularly in a place like Venice, which is right on the ocean, obviously, and it's going to get a lot of wind-driven rain. And then this same general idea is also done in masonry, but in different ways. So when they don't go to the trouble of corbelling the entire wall out. Sometimes the wall is planar, but then what moves out are those cornices. And that's actually the case with the Pantheon. So that might be hard to tell in that photo at the lower left, and it's kind of hard to pick a place on this building where the cornice is intact in 3 consecutive vertical locations because it's so kind of dinged up and chipped in a lot of areas. But it's very clear in all the reconstruction drawings that each cornice projects out beyond the one below. So they kind of made it work just by doing it with the cornices and keeping the wall planar. And then a similar variation on a theme, this is Palladio's Basilica in Vicenza, is doing it with flashings or with scuppers. So you can see on the photo at the right, these are almost like huge copper trumpets. And these were actually a retrofit, so they weren't original to the building, but were added, I think, in the 1700s to shed that water out. So a nice copper ledge at the first to second floor line, and then second to third floor line, we have these huge kind of copper trumpets, or doccione, as the Italians would call them. So onto the principles of durability. So I'd wrap up a lot of these as just water, water, water. You know, to kind of paraphrase the realtors, the 3 most important things in durability are water, 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 and how to manage water. And it was very clear to me, even in a place like Rome that has almost no freeze-thaw cycling, that that's the most significant factor. And the architects, the Italian architects I talked to there and the conservators, they said it was always about, almost always about water. So the way to deal with that is shed and shelter, and that's what we're seeing in those Tudor houses and in those step facades in Venice, and really even in the windows that we were looking at Palazzo Bronski, is the overall facade form, the roof overhang, that beautiful eave detail, the hoods, the sills, and all the ledges and the band courses on those streetscapes are all managing water and shedding and sheltering. So sheltering the most vulnerable areas and shedding the water frequently, at least at every floor, and often more often when windows are involved. And then choosing materials. So it's really not about using all the best materials everywhere all the time. So even the ancient Roman imperial construction, even Bernini working for the Vatican, they didn't have that kind of budget. They didn't use all the best materials everywhere. So they had to be smart about how they made choices. So it's really about making those choices wisely and allocating limited resources, which are limited materials and also limited budgets, in a smart way. So Ercolano, the stones of Ercolano, or Herculaneum, we would call it, they have 3 common stones in that area. They have basalt that's really super durable. They have a stone called tufo giallo that's really non-durable, doesn't hold up very well at all. And then they have a few things that are kind of intermediate, reasonable durability, not too bad, like tufo rossidus. And they used them all in just where they needed to be. So the photo at the lower right, the paving on these streets is basalt. So they used the best, most durable stone, not where they could show it off, but where it was really needed. So that was in the street paving. It's going to always be wet with the water between those curbstones. You're going to have hoofed animals going over it all the time. You're going to have carts going over it. So it's really going to take a pounding, take a lot of abuse. The second worst exposure are those curbstones. So they're not going to have the carts and the wheels and the hoofs rolling over them, but they're going to be wet a lot of the time, and they're going to see foot traffic. So those were the stones of intermediate durability. And then the walls of the houses, those were the least durable stone, the tufo giallo. And at the top right, you see some of that stone deteriorating, and that's actually what you can kind of glimpse in the photo at the lower right on the left-hand wall. That's a close-up of one of those areas. And that stone's really going quickly now because those roofs are no longer protected. So if you think about originally, all these houses had roofs intact, and basically they've left the roofs where they survived, and they haven't built up these shell walls to cover them. So the ones that are uncovered, like in the photo at the lower right, the tufo is really deteriorating. The ones with their nice overhanging 12-foot roof, as you can imagine, are doing very well. This is a Renaissance palazzo where they took a stone that the Romans knew was not very durable. Typically they only used it as kind of a backup with other facing or in an unexposed area, and that's peperino. So it's a very dark stone, very dark color, Maybe they wanted that color on this building. But in the photo at the two photos at the right, you can see how badly it's falling apart. So it's kind of like their equivalent of our brownstone. Doesn't hold up that well to the weather. They were smart for many centuries about how to use it. This building, someone didn't use it the way they should have. And even in that photo on the lower right, you can see that the vertical pilaster is still doing okay. And it's really those horizontal surfaces where the water sits and lingers that are just falling apart. Two similar stories, Palazzo Bronski, 1790, the three photos across the bottom, and the Villa Medici, 1544, which is now the French Academy in Rome. And this was a pretty unusual story. I found this first at Palazzo Bronski during the restoration, and I was kind of surprised to find the same story at Villa Medici. So if you think about putting a material in a position to succeed, they're building all these load-bearing walls. Some of them are going to be interior, some of them are going to be exterior. And obviously the ones on the exterior are going to bear the brunt of the weather, so they need to be made of more durable materials. So they built the walls differently. So the exterior ones they really built as well as they could. They used a very strong, very durable mortar with pozzolana in it, which imparts a lot of strength, kind of like a modern cement would. On the interior walls, they just used a very weak mortar, very weak lime, little or no pozzolana. And so even though the interior walls aren't seeing the weather, it's the interior walls that have all the problems now. So they have the mortar's all friable, it's kind of crumbling, the structure's settling, it's consolidating. So they're doing a lot of structural consolidation on the interior walls, and the exterior walls they're just leaving alone. So they kind of made the mark on the hard one, and they missed the mark on the easy one. And Villa Medici at the top right, they had the same issues during a restoration there within the past 10 or 15 years. Same story. And actually the real downside of this, that photo at the lower right, so they have some really beautiful and some very significant murals in this building that they had to drill through. So those are all drill holes, those white dots, where they're grout injecting these interior walls to stabilize them. The photo with the mortar in my hand in the center is kind of a nondescript one at the hallway that just had old crumbling plaster. It wasn't ornamental, so that was a good place to really get a look at that wall. Now, I mentioned Bernini, like most of us, didn't have unlimited budgets, even when working for the Vatican. So his beautiful colonnade at St. Peter's, he made good choices, and he put the money and the budget and the materials in the right places. So that colonnade is several bays deep, and I never knew until I got up on that scaffolding that the inner beams are all they're all faux. So those are all brick arches that are stuccoed over and then faux painted to look like travertine, and then only the outer beams are travertine. All the columns are travertine, by the way. But he put the material that was most durable where he needed it, and it was also aesthetically the real material where people would really get a good look at it and where it would be out in the sunlight. So smart choices. And the principle of durability for a particular material or component, say like a piece of hardware or something like that, it should really be proportional to three things. And those three things are the difficulty to inspect it, the difficulty to replace it if it ever fails, and the consequences of failure if it fails. So as a side note, these things often conflict with the typical approach to value engineering, where the person doing the value engineering thinks their job is to take money out but make the building look the same when the owner walks through. And so that's definitely going to push you to replacing stainless steel veneer anchors or stone cramps or something like that with hot dip galvanized, to then hot dip galvanized with electroplated galvanized, to then things just go downhill because no one ever sees them. The same with waterproofing and flashings. And it's very hard to get back to those things later without stripping the cladding off the building and all the scaffolding and access issues. So something like these two things. So these are two corroding hinges. One's from a 17th century building, one's from an early 20th century building. Even though they're corroding, I think they did okay, because this is right out there. It's easy to see. It's easy to replace. And there are really no significant consequences if one of these should fail. The door drops a little bit, people use the other door, and they replace the hinge. On the other hand, if you think of a structure like this, so any of the temples in the Roman Forum or in any of the Roman towns, really, kind of massive stone construction, way up high, so difficult to get there. These connections would dowel together. Sometimes down at grade on, say, a plinth or steps or something, you would see iron cramps or dowels used. The iron corrodes, but when you get into a situation like this, very difficult to get to, very difficult to replace if it ever fails. And then the consequences of the upper right photo, if those connections started to fail, the iron corroded and the stone spalled off and that came down, are catastrophic. So, and those types of connections, all I've ever seen are bronze dowels. Down near grade, if it's just something you're walking on, I've seen iron. So the Romans really knew where to put the money. And another principle, recognize and minimize inherent vulnerability. So even a good design is always going to have some inherent vulnerability or weak link. And I think the keys are to learn to recognize them, for starters, and then design to minimize your susceptibility to them, or the building susceptibility to them. So these are just some photos of the XGIL, which is kind of like was kind of like a YMCA by Luigi Moretti, a really fabulous early 20th century Italian architect. And on this building, kind of a less glamorous photo at the upper right of the roof of the gymnasium. He and Del Debbio, another great early 20th century contemporary architect, about the same time period, around 1933, they both had the same idea. And wouldn't it be beautiful to have these spaces illuminated by a glass block and concrete skylight, just this beautiful white pristine interior? And they both did it. And what Del Debbio did is he put his right on the roof. And what Moretti did is he knew that he was going to have a lot of sheet flow going across that roof and that would be vulnerable to leakage. So he raised his skylights up. So that's what you see there on the upper right photo. His glass block skylights are on those concrete drums. And Moretti's is still doing fine. I went in that building and looked up and didn't see any staining or signs of leakage. Del Debbio's, they're pretty much given up on. So the photo at the lower right, even though it's at a high point in the roof, the water's sloping away from it, they've taken to covering this with a translucent fiberglass corrugated panel, kind of built a little greenhouse over the thing to try to keep water off it. And that's what it looks like on the inside, all that kind of mold and staining on Del Debbio's version. So inherent vulnerabilities, another always inherent vulnerability are terraces over occupied space. So whether they're a Renaissance loggia or a modern terrace like in Thousand Oaks Civic Arts Plaza, you're always going to be vulnerable. And the keys are get the water off quickly, minimize ingress, and if possible, use moisture tolerant interior finishes, or maybe have a less sensitive occupancy below that space. So Pradock didn't do that here. His weak links were the seismic joints, and they were leaking really badly when we started repairing this building. So he didn't really follow any of those principles. The terraces over occupied space, this is really an unusual Renaissance building out in kind of farmland, a beautiful building, the Triangle of Barberini. And where the building steps back at that third to fourth floor, there are these terraces. And I was kind of amazed that they didn't really have waterproofing then, and I didn't know how they would make something like this work. So there's no sort of pitch or no sort of resin or nothing really that they used as waterproofing. It's just brick. But they did a few smart things. So one is they put a major slope on that. So it's about, I think it's about 8% slope to the drains. They had a short run to the drains, so they get the water off really quickly. They don't make it go far before they dump it out with these scuppers. And then they did a really smart thing, and this is typical on a lot of Renaissance and Baroque buildings. The way they set the brick on a loggia or a courtyard or some sort of ledge or band course was they would chamfer cut the underside, like you see in this little sketch in the center, so they can get the joints really, really tight. Because the mortar is a lot more absorptive than the brick. So what they're really doing is they're minimizing the area of the mortar because it's so absorptive and maximizing the area of the brick. So they wouldn't do this in other places, but they would specifically do it in those kind of waterproofing installations. Inherent vulnerability, wood construction is obviously wrought, and a high drying potential reduces that vulnerability. So this is a 1726 building in the Trastevere section of Rome. It's kind of the equivalent of a a hospital or a convalescing home. And if you look at that roof overhang at the right, the rafters out there were really doing fine. Inside the attic, where they had a lot of venting and air circulation, the rafters were doing fine, despite the leaky roof in both cases, a really old leaky clay tile roof. But right over the wall, these rafters sat right on the wall, and so without any air circulation around them, they were rotting right at that point and really nowhere else. Kind of a similar story on those EIFS or synthetic stucco-clad houses in the southeast in North Carolina and in Georgia. So 3 or 4 year old houses that are failing really badly with wood rot. The big story here was the drying potential. So they had interior vapor retarders. The exterior eaves had a pretty low drying potential, although it wouldn't necessarily be low enough to qualify as a vapor retarder, which was 1 perm. It was about 2.5 perms, but pretty low. So water would get in there, it wouldn't be able to get out, wouldn't be able to dry out. So this type of massive rot was occurring in less than 4 years, as I said. Right down the road, here's an old rickety wood barn, must be 75, 100 years old. That wood is definitely getting more wet than the wood on this house, which has the synthetic stucco over it. But it's much more able to dry out. So although that wood is split and cracked and that barn looks like it might blow over with a good breeze, the wood wasn't rotted. So, and the reason there is all about drying potential, built in a lot of forgiveness. Another principle of durability is deterioration happens. So we have to accept that. It's inevitable, and we have to design in a plan B. So a couple examples of that. At the left is not exactly an H.H. Richardson house. He allegedly did a little sketch on a napkin or something that Shepley, Rutan, and Coolidge later turned into this house after his death, built posthumously. But that similar detail of these kind of chinked stones, so lots of little stones shimming in between the larger stones, I've seen on every Richardson building I've looked at. And actually, if you walk in the undercroft of Trinity Church, you'll be able to see that detail's now exposed very beautifully in some areas. And that really looks exactly like the vernacular construction you would see on basically every little village in Tuscany has houses that look like this at the right. So the stones are shimmed in. And so what happens is if, and I would say when, the mortar inevitably erodes, then there's an alternate load path. So then all these stones aren't free to pop out of the wall. They're still wedged into place like they would be with a very well-laid drywall. And this is actually a Richardson building, and he really did have his hand in. So the Hampton County Courthouse, the stone on that upper part of that spire, which is about 120 feet up, they saw some cracking from the ground with binoculars. We went up there on a lift to look at it. And when we get up there, you see the opening at the center. There's really nothing left of the mortar. The mortar had just totally reverted to sand. But Norcross brothers, who built basically all of Richardson's buildings, they shimmed every stone. So they had the same kind of idea going on with stone shims or chinking as you see in the Tuscan construction. So even though all the mortar was eroded, none of those stones had fallen, and that tower is 120 feet above the entrance to the building. So it avoided a catastrophic failure. Similar idea in stone and masonry arches. So the Roman arches, you typically see a very tight joint. If they use stone, it's usually wedge-shaped. If they use brick, the joints are very tight, as you see at the upper right. And they may even be wedge-shaped, but even the rectangular, they basically meet brick to brick at the bottom. So the bottom line is, if the mortar erodes, you might get some shifting or displacement. So in the sketch in the center, you see that mortar erodes in the red line, the wedge drops a little bit, but then a new point of stability is reached, and you don't have a catastrophic failure of the arch. That's also what you see at the lower left photo where that's actually happened. That's the bridge at Palazzo Farnese, which is attributed to Michelangelo in Rome. So that mortar's washed out. A couple of the stones have dropped together, but then they've wedged into a new point of stability. And so there's no catastrophic failure. The photo at the lower right is actually on Blue Hill Ave here in Boston, and those bricks just fell out of that arch. And the contractor was telling me he had never seen that in 20 years. And what they had there was they had a very wide mortar joint. They had a brick that wasn't wedge-shaped, so when the mortar eroded, the brick just slipped right out. And that's also what you see diagrammed on the center sketch on the right-hand side. So even when using brick that wasn't wedge-shaped, the Romans avoided that by bringing those brick into point-to-point contact at the inside curvature of the arch, and that's what you're seeing at the top right. That's at Ostia Antica, the ancient Roman port. So while we don't build a lot of load-bearing masonry arches today, how is this principle really relevant? Well, it is relevant. This is a catastrophic failure in 1983, 3 fatalities right here in New England. This was a bridge collapse. This was a bridge that was built to federal highway standards. This was a common design detail in the day, and it was a pin suspended center. So if you can imagine in that diagram at the lower left, the right-hand portion is cantilevered. There's another cantilevered portion on the other side, and then there's kind of a simple span in the middle that just hangs off those other two. So by pins, so hence the pin suspended center. So what you have some steel pins. They're good size, but they're at a place where it's hard to ever see them. They're going to get road salt on them. How's anyone going to get there to inspect them? How do you replace them if you do need to? So all our kind of triggers of the durability of a component aren't met here. And then furthermore, what's the alternate load path? What's the plan B? If that ever does fail, what's going to happen? Well, what's going to happen is that span's going to drop into the river. And that's what happened. So that was really just a poor design. It's kind of hard to believe that we thought that detail was okay and that was a standard detail of the day, which it is. But if you run the structural calcs on that, you'll find that the pin is fine and it has a huge factor of safety as calculated, but no one's really thinking, or no one was really thinking, well, over time, what's going to happen? So in closing, I actually like to close with a few thoughts from Vitruvius to kind of come back to the beginning and come full circle. So he told us what qualities a building must have to be considered architecture, and he set the bar pretty high. Things, probably durability, I would argue, is the one that's being missed most often. Then it's really not architecture. And he's not even saying it's not good architecture. He's saying it's not architecture. So he set the bar high, but I think it's up to us to live up to that today. It's still a good measure of what architecture or good architecture is. And I just also wanted to thank the people that made this study and research possible, the American Academy, the National Endowment for the Arts, and SGH. And also what was really indispensable were the people, the Italian colleagues who were so kind to me and let me onto their scaffolds and onto their projects. So I just wanted to put their names up here for a minute. And then I'd love to take your questions. Yes, Susan. Oh, Leslie, I'm sorry. So I'll repeat the question in case the mic doesn't pick it up. So the question was, I've been talking a lot about water. What's my opinion of the new green roofs? Well, I guess they have some pros and cons, and it probably comes down to recognizing the inherent vulnerabilities. So one of the pros is you're keeping UV off of the membrane, and a lot of times, that can be an issue. You're also making the temperature more stable, and temperature cycling can affect, some of the roofing membranes as well. The obvious drawbacks are it's going to be harder to get to the roof if it needs repair, and then if the drainage system isn't really well designed, it could be subject to ponding water. And even if the drainage is well designed, it's probably going to be wetter than it would be if it were an exposed membrane. So it's definitely putting some performance demands on the membrane itself, and also on the need for us to design the drainage layers and the root barriers really well to make sure that those other things aren't really inhibiting the life of the roof. Yes? So the question was about our 19th century Boston building stock, thick load-bearing mass masonry walls, or the industrial. Okay, so textile mills, storage warehouses, things that are relatively planar facades. They don't have the projections. And what do I think about retrofitting some sort of rain screen panel on them or adding some projections or whatnot? And also the note that some of them have been leaking with serious wind-driven rain and some of the severe storms we've had the past 2 years. And I understand the year I was in Rome, 09 to 10, that buildings that really had never leaked of this type were showing leakage, so the rains were really severe. I guess the question, if they're always putting a cladding panel on them, can be a good solution for keeping buildings dry. And that's something we've done on a building where it didn't matter if it was the back alley of a building and no one ever really saw that facade, and it had some real serious leakage problems. And particularly buildings like that have, or early 20th century transitional masonry buildings that have steel framing embedded in the masonry walls. So that can be a good technical solution, but it's often not a good technical solution in an area like this in Fort Point, where you have some really beautiful historic buildings that are may have those characteristics, those technical characteristics. Another thing I've noticed is kind of the forgiveness of the interior finishes can really be a big factor. The investigative work I did on the old State House, they were having a problem in one corner of the building where the plaster was always blistering off. The other half of the building, they never had any problems. And what it turns out the answer was the east half of the building, the plaster was directly on the brick. So if the brick got wet, it was really susceptible to wicking that moisture through and blistering and peeling the paint. On the west half of the building, so that was the east half. On the west half of the building, it was furred off the wall with wood furring strips or other furring strips. And so what we suggested there, and and that was about 10 years ago, and what they implemented a couple years ago with that recent renovation by Talalian and Lee Kennedy, which was very well done, was they did fur that off in that corner. So by modifying the interior finishes, they were able to make the building more tolerant of the same amount of moisture in the wall without changing the appearance on the exterior side. And that's something we're also talking about on a building at UNH that I was looking at with Goody Clancy a couple weeks ago, where a lot of the water was being funneled to a couple points on the facade. The water was soaking through the brick and the plaster kept blistering and suffering damage. And actually in one area where the UNH staff had done some repairs, they had actually furred the plaster off, and it looked fine. So it was doing fine after all that time. The other thing are the materials too can provide tolerance. So gypsum board is actually pretty low on the totem pole of durable materials. An old style plaster tends to be much better. The paper face gypsum boards are particularly susceptible to mold growth. The paper facer is the food source for the mold, and then the gypsum board tends to retain it at kind of a moisture content that the mold really love. When you have a lime-based plaster, it's much more tolerant of moisture and not accruing mold growth compared to gypsum. Also, even some of the early 20th century lime and cement-based plasters on metal lath do a lot better. So the furring can do a lot to help, and also the choice of the particular type of plaster you use can do a lot to help. Yes, right behind.
Do you think we have a bigger challenge than the Greeks and the Romans because we have mechanical systems that keep the interior environment kind of at contrast with the exterior?
So the question was, do we have it tougher than the Greeks or Romans because we're creating interior environments that are much more different than the exterior environment? Great question. I would say yes. On a lot of buildings that were, say a residential building, it isn't that much of an issue. But where it's a huge issue is where we're really falsely mechanically humidifying in a cold climate. So when you have a natatorium or a museum in a cold climate like New England, those are kind of the poster children of building enclosure problems. Those are the types of buildings that need a really, really good air barrier. And every detail and connection needs to be needs to be really detailed and thought through. And a lot of times where they just miss the connection between roof and wall and ceiling, et cetera, then those breaches tend to create problems and almost funnel the moisture to one place. So a lot of times you look at a building like that from the exterior and you see a plume, just a plume of efflorescence in one spot. And that's probably telling you where some of the problems are. But it can be a double-edged sword as well. So those buildings, because of that real gradient between the interior and the exterior humidity, they need that air barrier. Buildings that aren't falsely or mechanically humidified or can run into problems actually. Sometimes when you have an overly tight air barrier and the building can't breathe or dry out. So even those eaves-clad houses, the synthetic stucco houses I showed down in North Carolina and Georgia, there was kind of a paradox there with the garage. So they had a vapor retarder required by code at that time in North Carolina in 1995. So these houses all had interior polyethylene vapor retarders right behind the interior finishes. The garages did not. The garages still had drywall, and a lot of times the garages had windows. So it was the exact same wall construction, and we were seeing that every time we made an opening beneath a garage window, there was less damage than there was on the interior. And so the garages, they couldn't dry to the outside because the eaves wouldn't allow it, but they could dry to the inside. The houses, they couldn't dry either way. So the moisture was kind of trapped between vapor retarders. And we've also looked at some buildings that are very, very, very tight, even residential buildings, but they aren't ventilated, and so they don't have much drying potential, so they can run into problems. So I think that can be a double-edged sword. Yes?
We'll get a follow-up lecture on how these principles actually work themselves out in good design in the 21st century.
So a follow-up lecture requested would be how these principles play out in the 21st century moving forward. Yes?
When's the book coming out?
When's the book coming out? I do have in mind to put this all into a book because I could see this as being very useful for getting someone thinking the right way about durability and design. And I think a lot of the materials or construction courses that I had when I was in school, they were much more focused on an individual material. These are the properties of steel, technical and kind of emotional, and wood is warm, and here are the sizes of 2x and nails. But they didn't really talk about principles of how to design. So I had to figure all that out on my own because we didn't have a course in that. So I think at some point I'd like to write the book that allows people to teach this and allows people to think about it and learn it on their own. Yes, in the back?
What are the special construction issues relative to freeze-thaw cycle climates like mid-Atlantic states?
All right, so the question was, what are the special design considerations for freeze-thaw climates like in the United States? Well, the basic principles of managing water become even more paramount. So you remember my water slide, I said even in climates with little or no freeze-thaw like Rome. And that was a surprise to me because so many of the material degradation issues that we would see here in New England on old stone or old brick relate to freeze-thaw. So water management becomes even that much more critical. And of course, material selection or putting the right materials in the right places also becomes really paramount. So the brick need to be well fired. I mean, so a lot of times when you do see very old, let's say 18th or 17th century brick, like on the old State House or other very old brick buildings, Hitchborn House, they weren't fired as long or at as high a temperature as they would be by, say, the 19th century. So those brick in the Back Bay tend to be doing better than brick on much older buildings like the old State House. But a lot of times you do see, our really durable Quincy granite is used where it really is going to get beat up. So just like they did at Ercolano, the steps leading up to the house on Beacon Hill, the first few feet of the water table before they go to the brick are that highly durable Quincy granite. I think if you saw brick in those locations, it wouldn't look very good after a couple hundred years.